What's up guys, welcome back to the channel. Today we're going to solve a partial fraction decomposition problem. So we have a rational function or expression, and we want to break it into different parts of fractions. To do this, we usually will think it as an algebra problem, or maybe something we'll do in calculus, such as trying to take the antiderivative of it, or maybe take a definite or indefinite integral of it. And in that case, we might just learn the covering method to try to break it into parts before we take the antiderivative. However, we have a 2 here in the denominator. We actually get a degree 2 term for one of the factors, so just the covering method is not enough. So this is also related to complex analysis, and in fact, our biggest tool that we can use is from complex analysis called the Cauchy's integral formula, and then the theory behind it. You can try to look it up online, or you can also try to find it from one of my old videos. So before we move on and talk about the solutions, you can pause the video, try it yourself, and when you're ready, we're coming back to see the solutions. Here we go. So we know that in order to break it into partial fractions, we will actually need 3 terms. First of all, we have the x plus 2 in the denominator, and then we will also have the x plus 1, and then x plus 1 quantity squared, since we have actually 2 copies of x plus 1 in the denominator. So for the first one, we can definitely use the covering method by covering the x plus 2 in the denominator and set the x plus 2 equals 0 to get x equals -2, and substitute in to get the coefficients of the first fraction. In this case, we get 2 times -2 plus 1 all over -2 plus 1 quantity squared. So in this case, we get -4 plus 1, which is -3, over -2 plus 1, which is -1 squared, which is 1. So in this case, we just get -3 here. So for the covering method, again, we can in fact try to extend it and use it for the terms that with the maximum exponents in the original expression. So in this case, we can also use it for x plus 1 quantity squared term. And to do so, we're just covering the whole x plus 1 quantity squared and set x equals -1 based on the part that we covered, and then substitute into the original expression without the part that we covered. So we get the numerator be 2 times -1 plus 1, which is -1, over the denominator, which is -1 plus 2, which is equal to 1. So in fact, we get -1 over 1, which is -1 here. Great. Now the question is, how do we actually do this? Well, if we try to extend it using a covering method or use the Cauchy integral formula, we actually will get the similar idea. We will still take the expression without the covering part, which is in fact the whole thing, x plus 1 quantity squared. So we actually end up with this expression here. Now, since we actually have the first power instead of second power, what we're going to do is we will take the difference of the powers that we have. In this case, it will be 2 minus 1, which is 1, and then this number is going to tell us how many times of the derivative we're going to take. And we're going to take the derivative of the expression that we have. So if we set this equal to some function here, and then we're now going to take the derivative of it, so that now we're going to find out the coefficients of the x plus 1 part. So in this case, if we're going to rewrite the expression, we actually get 2 minus 3 over x plus 2, such that if we take the derivative, we get, instead of negative, we actually will get a positive sign because now we only have the denominator. We can rewrite it as x plus 2 to the negative first power. So by power rule, we pull it out, so double negative cancelled out, and then the degree will become -2, so that we actually end up with 3 over x plus 2 quantity squared. And now we just substitute the x value, which again is just equal to -1, to get p prime of -1, which is the derivative of the expression that we have after covering, and also the coefficients that we're looking for will be equal to 3 over 1 squared, which is 3. And therefore we get our answer that we want.